Is now being recorded.
Good afternoon, everyone. Welcome to the last talk in our Spring 2013 Cyberseminar series. Our theme this semester has been complementary methods and models, with an emphasis on both how we collect hydrological data and what we can do with that data once we've collected it in different modeling frameworks. The voice you're hearing right now is Adam Ward. I've been the convener for this semester and last semester's seminar series. I want to first acknowledge the folks at CUAHSI who helped make this happen, in particular John Pollack and Kayla Berry. The two of them put in a lot of hours working with our speakers and making sure that Adobe Connect works flawlessly to get us all together from all corners of the globe. So our thanks to them for their hard work this year. If you've been on the line, you heard John start the recording. All of our cyber seminars are recorded, and CUAHSI makes these videos available to the public. Typically on Mondays after the talk, we get those uploaded online, so you can always go back and rewatch your favorite talks or look again to clarify that point that you might have missed during the seminar today. And with that, I'll give a brief introduction. Our speaker today is Dr. Marian Muste. Marian Muste received his Master's of Science in Civil Engineering from the Polytechnic Institute in Cluj-Napoca, Romania. After that, he moved to the U.S., received his Master's of Science and PhD degrees in Civil and Environmental Engineering at the University of Iowa. For 3 years, he held a postdoctoral researcher position at the Iowa Institute for Hydraulic Research. And since 1998, he's been a research engineer and adjunct associate professor through IIHR at the University of Iowa. Today's presentation by Marian Muste was invited because he does some cutting-edge work in hydroacoustic instrumentation, both how we can make measurements in the field and what we can do with those through new data processing techniques. And so with that, Marian, I'll turn things over to you. Let me get your screen share to the front. And we should be good to go. Take it away, Marian.
Thank you, Adam, for the introduction and for inviting me for the talk. Good afternoon, everybody, and thank you for attending this seminar today. In the next minutes, we will flip through an album of views of the rivers as sensed by several instruments operated by skilled people standing behind them. The presentation is aimed at synthesizing in-house work carried out for more than a decade, contributions from various partners with whom we collaborate, and obviously literature review, because the area is very dynamic and very dynamic and extensive. So I would like to thank my collaborators, of course my students, Dong-Soo Kim, Kyuta Lee, Howard Ho, and then some colleagues whom I asked to contribute some slides in order to make the points which I would Canada, Ricardo Supiani, University of Litoral in Argentina, Ramon Sanchez, person involved in measurements, field measurements in Ebro River in Spain. And I would like also to acknowledge the funding for several parts of this work by IHR, South Florida Water Management District, U.S. Corps, Chicago District, and U.S. Corps headquarters in Vicksburg. So we will talk a little bit about the context of this presentation, and obviously all of us notice, depending on the age, that the last several decades of advances in sensing, computer, and communication technology resulted in new instruments that regularly transform our capabilities to view rivers over a range of scales with unprecedented resolution. Most of these instruments are non-intrusive, which is great because a non-intrusive tool is a great advantage for an exploration tool. Today, for the present discussion, we will group these instruments in two families. I did it just for convenience because the instruments otherwise are very different in principle, scope, accuracy, deployment approach, cost, and so on. But for convenience, I grouped the non-intrusive instruments in non-contact. Here we have the spaceborne, airborne, ground-based radars, LiDARs, and image-based, and contact non-intrusive instruments. Here we have hydroacoustic and optical methods. Both of them, all of these instruments definitely are doing measurements on river with, as I said, various approaches. The non-contact tools are still under development. Many of them require extensive funding and support, and the deployment is quite involved. The contact, non-intrusive contact, hydroacoustic and optical methods per se, are many of them off the shelf. They are easier to access and operate. They have more accessible costs and well-documented protocols, so they can be easier adopted. That's why I would say I would emphasize this on these hydroacoustic instruments, which are uniquely attractive for quasi community because they are more affordable. They have tremendous potential for enabling understanding of many aspects of the river processes through in situ measurements, and they open new opportunities for fundamental research, which was many of these aspects which we try to investigate in the field were traditionally studied in laboratory conditions. Today's presentation aims at illustrating the new views of the river as enabled by non-intrusive instruments, and in the introductory part I will briefly go over several non-intrusive, non-contact instruments, which is not my area of expertise, and then we will gradually focus attention on non-intrusive contact hydroacoustic measurements. I leave the optical aside, and we will zoom in one of the most representative non-intrusive contact instrument, which is the acoustic Doppler current profiler, where we have a lot of knowledge. We can make the points of these new views of the river provided by this instrument, and really this instrument is accessible to us, and it offers a lot of opportunities for research, and also has some challenges which are very good subjects for research. Another reason to discuss the hydroacoustic instruments is the fact that I'm involved for about 10 years in this community, which is mostly dominated by the agencies, USGS, CORE, EPA, and so on. And the academic community is not so much present, despite that I feel, as a participant in the other in this existing community, that we can be more involved, and actually my presentation is a kind of invitation to get more involved. So we will start the presentation with non-contact, non-intrusive spaceborne and airborne radar measurements by presenting this set of instruments, actually, which is deployed from satellites hovering at about 800 kilometers in space, and they use interferometric synthetic aperture radar technology to sense the ground, basically the ground elevation, and based on those measurements, they can distinguish between water bodies and the terrain, and therefore they can delineate the river geometry, and they measure the water surface slope. Now, just using this information, in addition with customized slope area methods, type of approaches for measuring discharge, they are able to measure the discharge from space. Actually, this is the very ambitious goal, which is pursued now through this surface water and ocean topography SWOT program. The The scope of this type of measurements is to actually measure discharge at the basin scale, and then to be able to do budgets of surface water fluxes and water storage at the basin scale. As you see, the area of coverage of the instrument for one pulse is of the order of tens of kilometers. USGS also had an exercise with radars deployed from the ground through the Hydro 21 Task Committee, started in 1990s, and they aimed at this committee tried to review what's out there to make our surface water data collection more efficient, faster, accurate, and so on. Among the techniques which were tested, and I think that this was the this pair which you see AAB labeled in the figure was the only pair which was tested more extensively, because they have about 4 in consideration, is the ground penetrating radar and the surface Doppler radar. The ground penetrating radar using very simple principle of transmission of the radio wave pulses through the ground. They come from geomorphology word, and they can detect the surface water, the bottom. The surface radar, besides detection and ranging, they use Bragg cell scattering to infer the velocity at the free surface produced by small roughness moving with the water. With these two, they obviously, if everything is done as planned, they can obtain river discharges, and that was the goal. A new experiment of USGS involves a combination of lasers and mid-wave infrared and visible electro-optical imagery, equipment which is bundled, or actually the LiDAR is done separately, the imaging is done separately by in streams up to 1.5 meters at this time. They allowed mapping the bed, obviously the ground, but also penetrating to the water and providing the bathymetry information. With the imaging technique, using infrared camera, they can detect the velocities at the free surface, and then combining the two, they obtain the discharge. A technique which we pioneered here, which is from the image-based measurement starting in 1996, is large-scale particle image velocimetry, which is a non-contact, close-range technique using simple video images taken of at the free surface of the river, and then using image pattern recognition and statistical inferences, we can determine the distribution of the flow at the free surface. And then with known bathymetry and the conversion factor from the free surface to the depth average, which is used by other techniques too, non-intrusive techniques, we can obtain the discharge. So all the above presented technology and instruments continue to be developed and validated, but as you can guess, their costs and deployments are considerable, and they are beyond the reach of the academic settings. More affordable are these non-intrusive contact measurements, which are covered by the hydroacoustics and optical instruments. Definitely these tools require deployment in the river, and from the two we leave aside the optical instruments, which usually are used to measure suspended sediment or other particulates in the body of the river. And we will focus on hydroacoustics, which again I am a proponent of them, and that's the point basic of the discussion, feeling that we have a lot to give to these kind of developments. The hydroacoustics are commercially available, increasingly accurate, robust, efficient. They are very safe, as you will see. They were originally developed for hydrometric measurements in various conditions: shallow water, deep water, normal, high flow, smooth, rough bed, very adaptive to the measurement environment. And they are capable for providing very nice new insights into fundamental aspects of river hydromorphodynamics and their interface with other disciplines such as modeling, ecology, and so on. The talking points from now on will be on the capabilities and limitation of the S-design instruments, highlighting some additional capabilities enabled by customized tools and protocols developed here, of course, but then in other places too. And then some perspective in putting together what was developed and integrating that information on rivers in the watershed landscape. So that's what we plan to discuss more in depth in the next slides. So, as I mentioned, hydroacoustic instruments were originally designed for hydrometry. They were brought in the riverine environment in early 80s from coastal research. The targeted measurements at their transition to inland river was to get discharge and bathymetry. They become very popular and they continue to be, they actually replace the conventional instrumentation for bathymetry and discharge at a very high pace, championed by USGS. You see on the graph on the right that USGS is currently doing stream flow measurements with hydroacoustics in the proportion of 67%. I think that number is now 70 or 75 already. They are very well known instruments to this agency, and we can benefit by good documentation about the measurement protocol, maintenance, verification. And I can cite here WMO has a lot of a new manual on stream gauges which has this technique well described. USGS and Environmental Canada has very good literature on these topics, and a good site to keep updates is the hydroacoustic USGS hydroacoustic website. Now, going more in depth about these instruments, the hydroacoustic instruments measure depth and velocity. The depth is measured based on the echo detection, a very simple principle, I don't go through it. The velocity measurement is based on detection of the Doppler shift, which actually assumes to send a pulse of known quality and the characteristics in the water, and then at the propagation of the while this sound pulse is propagating in the column of water, it interacts with the particles, and the backscattering coming to the receiver located in the same place with the speaker will detect the Doppler shift due to the Doppler shift which is produced by the moving particle in the sound along the sound path. Now, comparing the original frequency with the shifted frequency with this relationship, which involves only the speed of sound, basically, and the characteristic of instrument, we can get quickly we can get the velocity of the scatter in the water. The instrument measures along the beam, only along the beam, the component along the propagation path. So if we would like, actually let me go to the limitations. So and I will come back to this point. So this some limitations are involved with these instruments, which is obviously the contact requirement, and then the fact that they measure on scatterer. They actually, without scatterer, they don't have any measurement. Too much or too little creates problems. And then, because we measure just one velocity component from one beam, we usually the instruments have They cannot measure very close to the transducer and near the boundaries. And the spatial temporal resolution is good, but it's variable depending on the characteristics of the instrument. I can provide more details. The hydroacoustic depth measurement, I have two slides here. Very quickly I go through. They are very straightforward. The echo sounder, the single beam echo sounder measuring, deployed on a boat, and boat which is hovering, is cruising the river, can get information about the bathymetry. The more, increasingly more used is the multi-beam echo sounder, which produces a narrow along and wide across the boat track beam, such that we get information about bathymetry in a SWOT, and that increase extraordinarily the performance, the efficiency of these tools. Information provided by these instruments are very valuable, very accurate, and very comprehensive. We obviously get very good information about the cross-section. By doing cross-section over reaches, we can get information about Talvik line, other aspects of the cross-section. Going at the reach scale, we can see riffle pool mapping. And then the MBS has another capability, which is the functionality of a side scan sonar, which allows to distinguish the texture, not the texture, the material which is on the bed. So looking at other properties of the sound wave, of the echo, you can differentiate between gravel, sand, debris, other structures which might be on the floor. Now moving to through conceptual sketches at the acoustic Doppler velocimeter and acoustic Doppler current profiles, ADCPs. The ADV measure in a point, non-intrusively in a point, and they provide three velocity components. The HADCP, which is the second slot here with sketches, measure along the line of sight using two beams. On the side, they can be deployed at the bottom and looking vertically, so there are various deployments. The ADCP deployed by the boat is another actually this is what I think that is very close to our home in terms of research. The ADCP, this ADCP is mounted on boats, and the boats cross the river in typical perpendicular cross-section or other arrangement, as you will see, depending on the purpose of the measurement. But in essence, the ADCP provides depth, to provide velocity distribution in the water column, which is a kind of instantaneous velocity profile in the axis of the measurement. This information is obtained by using the velocities in the four beam, diverging at in four different locations. The velocity in those beams are combined to obtain the velocity in the axis. So here are the assumptions which, if the flow is very three-dimensional, will not give you a very good result. But usually they are very robust and work well. Now, from velocities, by wading, fixed deployment, or transecting the river with these instruments, you can get the discharge. There are two methods to use the ADCP, as I mentioned: moving boat measurement and fixed boat measurement. Where you do more conventional measurement, you go cross section by section, and then the software the software will put together all that information and come out with a discharge. You see nice displays of the river with a measured area near the boundaries and the measured area in between. Now, these instruments are efficient, as you see, in terms of accuracy. If everything is done right, we get very good data, data which actually is within the accuracy used by or recommended by monitoring agencies. And as an example, I provide here an uncertainty analysis conducted with a rigorous uncertainty analysis standard, GAM 1993, where we did some assessment of the element. First of all, we identify all the sources of errors, and then we assess some of them which were not covered in the literature, and we use other information available in standards, and we get to an uncertainty of 5.8, which, as I say, is quite within the requirements of the monitoring agency. I think that for very good conditions, is no problem to get 3–4% uncertainty in the discharge measurement. I wanted to spend some more time, I ran out, about this uncertainty analysis, which is a very good research topic. It has a lot of need in terms of development, so there is a lot of activity going on there. Now, one of the main roles of ADCPs in general is to support the continuous and real-time discharge estimation. What you saw before are direct discharge measurement, that was the illustration for. But with, as you know, with the stage discharge rating curve methodology and another one which I will refer on next slide, we can actually build some rating curves using periodic measurements of discharge with these efficient tools. We build rating curves, and then by just continuing measuring the depth, which is cheap, safe, and so on, at the gauging station we obtain the discharge. The contribution which is brought by the new instruments is right here, that technology, conventional technology, were not could not be deployed in difficult conditions, high flows and so on. With ADCPs, you can go all the way to flood situation. The last point which I highlight here is taken during the flood of 2008 on Iowa River, so very hostile conditions. So ADCPs allows us to do this measurement. A more important area, and we are now involved very heavily in analyzing this aspect or this capability of ADCP, is to do event-based sampling of the discharge. The assumptions which are related with this one-to-one relationship between discharge and stage are assuming the steady and uniform flow condition. During any rain, during any flood, the flow is unsteady, and then the things are much more complicated, meaning that from on a hydrograph like this, with the steady assumption, the Qmax, the depth average, and the cross-section velocity, Qmax and Hmax are occurring at the same time. In reality, in an unsteady flow, you have a sequence like shown in this figure. Umax precedes Qmax and Hmax lags Qmax. So these cannot be captured. Now, most of the inland river in U.S. are treated with a steady, uniform assumption at the rating curves. Only very special places prone to floods on large river are tracked differently, either analytically, either through monitoring. And when you do that during flood, you will observe that the rising and falling limbs of the hydrograph have different curves from the steady curve, and this can be interpreted like conceptual bias in the rating curve if you would like, or can be used in various ways, forecasting and so on. The index velocity rating curve, another option for measuring discharge, is actually was developed, I think, for acoustic techniques in the beginning, but it was on the first acoustic techniques. Right now, they are increasingly popular with the increased use of the ADCPs, which are deployed on the side or on the bottom, and they measure an index velocity at their location, and then we also measure Q through direct measurements, periodic measurements, to obtain a rating curve, and then we measure the cross-section. We develop these two rating curves, the stage area and the V-index, V-mean area, such that we can obtain right away the discharge. Now, two measurements are taken simultaneously, V-index and H, so that is an improvement or an advantage in capturing unsteady flow events. But to capture the unsteady flow events, we have to look more attentive in what happens with the velocity, which is our main variable, a second main variable which we measure here, a second variable which we measure here, and keeping in mind that during a steady flow, the velocity profiles are departing from the steady flow profile. So that will also produce a non-unique rating curve in index velocity, and that is generated by this non-unique relationship between H and Q. Now, hysteresis is nice from the research point of view, but we don't know exactly, which is another topic of research, how important it is, because it's typically neglected in small rivers, but we had here some exercises on using analytical methods, and we look at a small stream in Iowa, and we learned that during a 1 year type of storm, we got difference in discharges from the rating curve up to 10%. This 10% exceeds the 5% considered acceptable by agencies and typically associated with the measurement uncertainty. So the point is that we have with these tools capabilities to measure more often and to look at the impact of this unsteady flow, doing event-based sampling, on the accuracy of the rating curve, because if you take a measurement periodically like USGS is doing, every year there are 6-8 measurements not correlated with events. They target the large events and they go for the highest flow, but it's not a continuous tracking of the event, which has some importance. When you do that, you can see what this team from Spain noticed during a flood of about 3 days. They did 28 direct ADCP measurements, about 30 minutes interval apart, day and night, and they were able to capture the loop rating curve. All what I presented before is conceptual, by also demonstrated in the lab by many papers. Many, I wouldn't say many, but they are backed with experiments in the lab. Now this can be done in the field, and what we saw in the previous slides, we saw it here. This is a real loop rating curve captured by the ADCP with those multiple measurements. And you see, this is the steady rating curve, and you see deviation of 40% during the event from limb to limb. Maybe it's 20% from no, actually it's half from steady rating curve, which is our guiding line, and also similar differences in Hmax for the same Q. We also see that separation, which I noticed in the results obtained in the lab. The loop rating curve also, if it's done with event sampling, we'll see some particularities. Basically, there is a loop in the stage U mean U across the section, as shown here for this same flood, and that loop is generated by some changes on the rising and falling stages of the propagation of the flood wave. Now, overall, if you do it with the HQ with discharge stage relationship, you saw it several times, this one, and then here is the same plot, HQ, provided by the index velocity. You see that it appears disregard of where is the point of observation across the stream. This is an index velocity based at the ADCP at 4 meter. This is at 6 meter from the surface. Now, these are proofs that with proper planning and so on, the ADCPs can be, the rating curves can be captured, and still, because of the effort which is involved with this type of measurement, there is need first to find out some diagnostic formulas in order to know when these measurements are needed, because you don't do it, it's impossible to be done at all the places. But my point is that currently only large rivers are covered by some more efforts along this line, and we have a lot of floods in smaller rivers or medium rivers like Iowa and Cedar rivers produce floods almost every decade one. So for these events, we think that looking more carefully at the rating curves will be able to move from the typical steady rating curve fed as boundary condition in steady hydraulic models. We can move to loop rating curve, and with unsteady hydraulic models, we will be able to get inundation maps which follow the actual physics, and more importantly, the timing is captured by this method because they associate this difference in Qmax, Hmax, Umax can be detected and also kind of used for mitigation purposes. So I just insisted a little bit on this one because I think that's a good research area, and having this differentiation between the rising and falling beam has more aspects on shear stresses in rivers, transport processes, so it's a good area of research. Now I would like to provide some more views of the ADCPs. As I mentioned, they were developed originally for discharge, but they actually measured tons of data in each individual cell in a Mississippi River, in a cross-section here in Iowa. You have about 8,000 vectors in a cross-section, and these are vectors with 3 components. They are instantaneous. You can get a lot of other information, and this information can be obtained in various ways, Lagrangian or Eulerian investigation framework. So we really can do a lot of research in situ. So the next slide will show some of these views obtained with the ADCPs. This is Mississippi River based on transects. We go bank to bank, quite in a straight line. We can have this view of the river. Then we can reproject this on nicer profile, which are used for validation of numerical simulation. We can visualize depth average velocity like here. We can compute shear stress and map the shear stress on the bed from the same measurements. We can put all these measurements in context, in GIS context, to make use for practical purposes. Adam, I'd like to know how much time do I have? I'm kind of
yeah, so it's it's about 2:40 right now, Marian. If you wanted to try to take, say, 10 to 15 more minutes for your talk, that would give time for a few questions. Before
Okay. I plan to go fast, but I'm a little bit behind. Okay, so these are some views of the rivers which are not using, it's basically the same what you do for discharge measurement is done here, but then some processing is needed, and obviously that's an additional effort. Other views from my colleague Colin Rennie in University at Ottawa are geared to bathymetry and bed load velocity mapping using an Eulerian framework. So in this case, as you can notice from this figure, from this sketch, the trajectory of the boat is different. It doesn't go very nicely. It goes in these zigzags and cover quite well the bed. Colin used and others are using by having some extra tools on the ADCP, which are pretty cheap, a GPS, you can sense the movement of the bed as measured by the ADCP. Another view of the bed form evolution, and can be approached this evolution from Lagrangian or Eulerian frameworks, and further move to estimation of bed load, comes from Riccardo Suppiani. He has extensive work on Parana and Amazon, and these are some measurements in Parana River where he captured, at 2 days apart, the movement of the dunes, and you can do a lot of things with it. He continued to use this information to estimate the bed load transport. Another view of the river, and actually a very active area currently, is estimation of suspended sediment transport from the same ADCP, and it can be, it's obtained simultaneously with the bathymetry and the velocity measurement. Now this is, there is a small community actually working intensively on this subject of determining the suspended sediment from ADCP measurements, and here CUAHSI had a very nice workshop last year in March where USGS and other agencies and CUAHSI had a workshop on sediment hydroacoustic techniques for rivers and streams, and experiences and new research and validation projects were kind of streamlined. The method works, but there are many things until to be sure that the things are as you would like to be in terms of accuracy, and to not be dependent on some calibration which these type of measurements require at each site. So I hope that the examples above have demonstrated that these non-intrusive instruments, and close to our home, our hydroacoustic instruments, can transition a considerable part of our research from lab to the field. In the lab, we used to do very detailed research on mean flow characteristic, turbulence characteristic, using both the Lagrangian and the Eulerian approach. Now, this is not anymore a no-no for the field investigations, and currently ADCP are able to provide the velocity in the water column, some information about the bed movement. They can, as I showed, measure suspended concentration. They can do something about bed load. So really, we can have water quantity and water quality, water quantity and sediment transport kind of analyzed with the same tool. This is a great dream for a river hydraulic researcher, to have one instrument, one deployment, and to get so much data. Now, all what I showed before requires some, besides acquisition requires some processing, which at times is very, you know, not straightforward or require additional effort. We started in 203 here some kind of synthesis of methods, and we look at the instrument, we look what can we extract from the raw information, and we develop a software to show you these tools. They are using they are fit at this time for RDI instruments, but very simple scripts can be done to be adapted to other ADCPs, because there are about 4 or 5 types of ADCPs currently on the market with various prices, capabilities, and so on. So this software was one of the first, but there are other softwares also available in various places. There is no software attached with the instrument at this time from the manufacturer. This is something to point out. But with this software, we were able to do fixed deployment measurements and get a nice velocity, mean velocity profile, which fits the log law. This is, I think, from Florida. We can get turbulence. Turbulence intensity is questionable in terms of accuracy, but we can get Reynolds stress, and we can get TKA easier. And everything is not so straightforward like I show on these plots, because we have to look what and how many beams to use in order to extract other than the mean velocity. This uses all the 4 beams, but for other quantities we have to take into account that limitation that turbulence cannot be sampled in 4 points and assumed to be homogeneous in the axis. So there are some things which we have to take care of, but more research can be done here along these lines. Then we have these measurement tools for analyzing ADCP transects, you know, to use spatial averaging, because we get these pings at a frequency of 60 Hertz, and then if the flow is uniform from this vector to the other one, you can average over that. Let's say that it takes 1 minute or 2 minutes to travel this distance. You can average the flow field to get a smoother velocity profile, which you can consider equivalent to a time average profile. Then with this type of information, you can do now other things to put the vectors in string coordinates, to reproject, and to do other things. To visualize, and here is an example of visualizing secondary flow, which otherwise are very difficult to be captured with a point instrument that just imagine. And this type of view can be obtained in 15 minutes of travel across the Mississippi River. Then other algorithm which I mentioned before, getting the bed load velocity was incorporated in the software, getting the bed shear stress by analyzing the data, and get the dispersion coefficient from ADCP measurement, and I will come back a little bit later with some example. And obviously bathymetry is there. This is survey of Mississippi, so bathymetric survey of Mississippi as provided by ADCP, Rio Grande ADCP. Of course, here again, in order to get better data, we look at the situation, we look at the instruments, and we use in the software some things to get the best results. Uncertainty can be well embedded in this type of tools, and what you have here is actually a standardized approach applied to the ADCP measurements, and you have here what is the map color. The map shows is uncertainty in each of the bin of the ADCP ADCP. And also, what is important, and I forgot to mention before when I touched on accuracy, if you use a rigorous method, you get this type of, you get 2 things: confidence level in estimation, which can be done at various percentages, and you get the relative contribution of various elemental sources to the total uncertainty, which is extremely important information for learning. Do you have to improve the operation? Do you have to, the site is not okay, the instrument is not okay, and things like that. That's the value of this information. Now, everything goes well, data is accurate, but as I mentioned, handling the data, the vast amount of data is quite challenging, and we need to again think ahead of what we'll do, because more and more tools like this producing gigantic amount of data will be focused on river. I just invented several, and you imagine that it's an ocean of information, which makes the processing, extraction of information, knowledge from data very time-consuming. So we need to organize, and this data model will help us. The data models will help us to go in that direction, where we can ingest various, various instruments, various instruments in the same data model, and kind of look at our variable of interest. So we started with Dong-Soo Kim in 2005 to look at a data model for the river. We call it ArcRiver, but definitely it was inspired by the work of Maidman done with ArcHydro and other tools like the RCMM developed river channel morphology model developed by Venkatesh, and then we both use the concepts which were used in these previous tools, and we try to connect to them, because the hydro network defined, from a LiDAR data in stream axis is a very good point to start building our 3D model, which takes now the measurements in the volume of water and connect with the hydro network. Again, the tools for bathymetry are very useful to and complement constructions like this. So we got some advancement, but there is much work to be done on these data models for the river. They allow us to do 3D representation of the hydromorphological features, exactly like a tech plot does from numerical simulation. But this time we feed in the data model measured data, which is extraordinary. I mean, it's extraordinary meaning that it's a nice repository, which otherwise is very, I don't know exactly what is done by the best in the field, but I saw just with what we process here how difficult it is to work with folders and so on. So this ArcRiver model was built on top of ArcGIS, handles scalar, vectors. It has all the goodies which you might expect from 3D models, at least we tried. And starting with this information, the model was developed and triggered and developed around ADCP data. At this time, we cannot ingest other instruments, but the couplers to other instruments, from other instruments to the data model, can be done easier anyway at the beginning. So ingesting this type of data, we can then project that data on grid. We can project the data on planes and look for volumes, for streamlines, and so on. More than that, these models allow some representation of processes, like it's shown here. Using ADCP measurements in Mississippi, we determine from the ADCP measurement the dispersion coefficient due to the distribution of velocity across and in the verticals, and then we can plug in a small dispersion equation here to simulate what happens if we have a pollutant at this end in terms of propagation with respect to propagation in space and time. Another use kind of case study we did with the same model on some laboratory data with acoustic instruments, where we have movies of this bed evolving as measured during some experiments. There is no limitation to move this directly to the river. So if we take advantage of what is out there, we can think of a river data model which connects all this information in the digital world, and then definitely we can help many areas, research, decision-making, knowledge discovery, all fed by the same good information, good measurements, if this work is kind of coordinated in any shape and form. So this can be taken further. CUAHSI is very well known, and it was inspiring for us in developing platforms for watershed. We have one for the Iowa, where we have layers from USGS, EPA, and so on. We have our own instruments. We have online data, of course, for many variables. I'm looking ahead at the day when I will click on Iowa in a surveyed reach with ADCP, and I can see historically an event, I can see an event measured by ADCP in a special event, which I try to show here. So my conclusions are that hydroacoustic as well as other new non-intrusive instruments are mature enough to be embraced by our community for enhancing our views of the river through in situ experiments. There are many fundamental research opportunities in hydrologic science and other river-related disciplines that can considerably benefit from the increased adoption of these instruments. And we have a very good position to move more aggressively the adoption and the use of these instruments, because we have, we have this program, HMF, we have access to USGS, which is an extraordinarily useful and powerful and knowledgeable source of sharing information about hydroacoustics, such that to move ahead with new research with these instruments. So that's my presentation. Thank you.
Thank you very much, Marian. This is Adam again. And perhaps the only unfortunate part of these cyber seminars is that you can't hear that all of the people on the line are clapping right now in appreciation of a great talk.
I'm sure.
So thank you on behalf of everybody on the line.
Thank you.
So, Marian, it's just about 3 o'clock. Do you have time to stick around for some questions?
Sure.
Great. So for folks on the line, what I typically do is ask that you would type your questions into the chat box. You should see that on the bottom left-hand side of your screens. And we'll ask Marian to address any questions that you have in the order that they're asked. And you can, when your question comes up, feel free to unmute yourself by pressing *6 so you can have a dialogue with Marian if you'd like. And Marian, I'll take the privilege of maybe asking the first question while everyone else is typing here. I was really intrigued by many pieces of this, the coupled quantity and quality data, what we can potentially do with these data. One of the more direct applications seemed to me when you were talking about floodplain mapping and moving from steady state to unsteady state models. I guess my question is, what does it take for us to do this? Is it simply having these dynamic rating curves, or is there...
Now, okay, what I see, and I have with me Cuter, who is working on the hysteresis. What I see here, we use unsteady hydraulic model, not very often, for special application, of course, dam breaks and so on. We use unsteady hydraulic model and in other situations. But we do not have, for medium rivers, we do not have the loop rating curve, which usually is boundary condition for the model, So we use the rate at the boundary condition, we use the rating curve, the steady rating curve. Now, as I say, I don't want to make a big case that hysteresis is a big issue. No, it needs to be assessed, and that's another work by itself. But when you feed a loop rating curve as boundary condition, your model will have another trajectory in time. You end, as you see here, or here, maybe here, you see you end at the same Qmax with both, but it's about the trajectory from Weyer's approach. When you come on the rising, you have another dynamics than this one, and when you are on falling, you have another dynamics, or the relationship between these two relations. What is in my mind the importance of this observation, we can detect maybe not Qmax, but not Umax, because that means velocity measurement in the river during flood, but we have we sense Qmax from the existing gauging stations, you know. No, sorry, maybe I'm wrong. We have to do something to use this trigger, to use this as trigger. Yeah, we can sense when the velocity decreases. And then we will know that from this moment to this moment, there's some time when you still have some lead time to build further the levees or not, you know. These are data. We don't have all the implications. At this point, we just look if we can capture it in real conditions, and there is more work to be done on the implications. But in my opinion, this is a big difference to have velocities 20% higher on the rising than on the falling. This is more important for transport processes, habitat, all that, anything which is related to shear on the bed.
Okay, thank you. Thank you, Marian. Let's see, and anybody else on the line here have a question that you'd like to ask Marian? You can either type it in the box or press *6 on your phone to unmute yourself and ask him directly. We'll give just a few moments for folks to type in anything they want. Well, Marian, seeing no more questions coming in, I think we'll wrap things up here. So again, on behalf of everybody on the line, I wanted to thank you again for your time. And thanks to folks for tuning in this afternoon, as well as those of you who are regular attendees of our seminar series. As I mentioned at the start, this is our last seminar for the academic year through the Cyberseminar program. So watch for announcements from CUAHSI over the summer. We'll have a new theme and a new convener next year, and those presentations will begin, I